Alright, this video we'll check out a couple rational functions examples here. I do have some work already worked out because I kind of wrote it off to the side, but this is part one of a three-part video because our end goal is to graph these three. But there's quite a bit of background work involved in each step, and I didn't want to create a 2-hour video, so I'm breaking it down piece by piece. And first we will look at domain. Okay, with domain though comes in a graph, it comes vertical asymptotes, or it could be holes in the graph. So how do you distinguish which one it is? And if you've never heard of those, like what are they? So we'll look at both things as we go through here. All right, so the original problem is in black. A rational function just means that, and we're looking at polynomial functions that are rational. So that means we have a polynomial function in the numerator and one in the denominator, perhaps rational. Remember, just means a fraction. So they are still a function. They would pass the vertical line test, but we may get some things to cancel once we factor. All right, so in blue, f of x, g of x, and h of x, I'd factored all three of these. Okay, I didn't want to do a video about factoring, so I just went ahead and factored them before I started. And you notice in f of x, the first one, we have x minus 3, x minus 1 over x plus 1. Nothing cancels, right? We can't simplify this at all. And in terms of vertical asymptotes or holes, we need it factored to see if anything does in fact cancel. All we are concerned about is the denominator for vertical asymptotes or holes. So what do those mean? First off, a vertical asymptote is, and we've all seen them, but it's part of a graph. Say we had this, and we've dealt with a parent function of 1 over x, and depending on the reflection or the shift or whatnot, right, that I'm just going to graph very rough sketch of parent function 1 over x. The vertical asymptote is this line, this vertical line that the graph would never cross. Okay, opposed to a hole, this function might exist everywhere except for maybe one point. Okay, and we'd put a hole in the graph there, but there might be several holes. Okay, so at that point, whatever this x value is that I drew in here, for instance, might be a hole. Where the vertical asymptote, the graph approaches either infinity or positive infinity on the y-axis, but it will not cross that vertical line. Okay. In a function, algebraically, the difference is this. In this first one, if I set the denominator equal to 0, I know that x cannot be negative 1, right? That is not in the domain. X cannot be negative 1. And this is, in fact, a vertical asymptote because nothing canceled in this problem. So if we were to write domain, we usually write it in interval notation, although I really oftentimes like to say what the domain is not. If x cannot be negative 1, it could be any other real number, right? But in interval notation, which is pretty common in a math class, we say from negative infinity to negative 1, parenthesis means we exclude negative 1, but then we start back up to infinity. Okay, that excluded negative 1. But the vertical asymptote, I'm just going to write VA, is x equals negative 1. Okay, if I were to graph this, I don't know anything about this graph at this point, except that at negative 1 here, okay, at negative 1, wherever that graph is going, it will not cross that vertical line. Okay, we'll look more at the graph later, but that is how we go about this. Okay. In g of x, notice we have a common factor, x plus 3 in the numerator and denominator. It cancels. Now, a common mistake is not excluding this from the domain, just counting it as if it canceled, and if you went on and just graphed x minus 1 over x plus 1. But this original function is different than the simplified one, right? In a sense. They're the same function, one is just simplified, but -3 is not in the domain. Okay, when I set x plus 3 equal to 0, or it cannot be 0, right, technically, x cannot be -3. And also x cannot be -1 from the x plus 1 factor. But if you look at the simplified version, there is, right, -3 is not a restriction. So we have to keep that in mind when we go to graph this. And it's easy to forget about, but we actually would end up with a hole. Okay, there is a hole at x equals -3. Again, I don't know what the graph looks like off the top of my head, but I know wherever x is -3, there would be a hole. So, if I pictured the one above here, if this were -3 and I put that hole there, okay, that's what that would look like on a graph. Okay, let's continue to answer this. So the domain, x cannot be -3 or -1, so we go -infinity to -3, and then it starts again -3 to -1, but then there's another problem, right? And then from -1 to infinity. So we have two problem areas, one at -3, one at -1. Because the factor x plus 1, this factor did not cancel, that's a vertical asymptote. Okay, the vertical asymptote is x equals -1. That was just coincidence that the two problems I chose had the same vertical asymptote. That's no big deal. And then, like I said, the hole is when x equals -3. All right, and again, we'll look more at graphing the entire rational function later, but for now, we're going to do pieces. So there's everything about the domain, vertical asymptotes, and holes for the second one. All right, this third one. Always look for a GCF. In the numerator, there was only an x that I could factor out, right? And then the denominator, I could also factor it out at x, but then it factors more. So rather than writing it all over again, I just write the factorization right below. Now, only the x cancels, nothing else cancels. Remember, if it cancels, there's a hole there. So when x is 0, there's a hole. And then in this problem, we'll have two vertical asymptotes. I got to set that equal to 0, that equal to 0. So there's a hole when x is 0, and then the vertical asymptotes occur when, if I solve this, subtract 1, divide 2. So vertical asymptote at x equals -1/2. And the other one, I'll go ahead and do it, but we could just do that in our head, right, when x equals 3. Okay, two vertical asymptotes, one hole. And again, domain, well, now we have three problem areas. I'm going to give myself some room for this one, because the domain, to write in interval notation, it's quite tedious, and that's why ultimately I like just saying, you know what, x cannot be 0, it cannot be -1/2, and it cannot be 3. But interval notation going in order, our first problem is -1/2. Union, we start back up again, up to 0 is the next problem. Start back up again, 0 to 3, and then nothing else from there forward, 3 to infinity. All right, and then to recap our answer, there's a hole when x equals 0, and then vertical asymptotes at x equals -1/2 and x equals 3. Alrighty. One last thing I want to add in this video is to get it a little more precise. So I said the hole is when x equals 0. But like, where exactly is it? what you can do to find that is, so the first one didn't have a hole, so we'll look at this second one here, is plug that -3 into the simplified version. So if I did -3 in this here, I'll keep with pink, g of -3, we would get -3 minus 1 over -3 plus 1. So that's -4 over 2, which is -2. So the hole occurs, now this is the y value, but it's still, remember, it's undefined there. So the hole exactly is at -3, -2. Okay. So same thing with this h of x. I had a hole at 0. So if I plug in 0 into the simplified form, h of 0, I would have 0 plus 3, and then plug in 0 in the denominator as well. So 0 plus 3 over 2 times 0. So I'm going to just do that in my head. 2 times 0 is 0 plus 1 times 0 minus 3. So we get 3 over -3, which is -1. So the hole is 0 for x, but -1 for the y.